Hello, this is Xtal. In today's tutorial, we will be creating a digital embroidery cross-stitch effect together inside TouchDesigner. The network we'll build is based on a pixel-driven grid, generating stitch patterns and remapping the original colors to produce a texture that feels like real, hand-woven thread. I will walk you through each part of the process, explaining what every node does and how the entire pipeline connects, so you can follow along comfortably and later refine the pattern into your own unique style. First, we import the footage that we'll be using as the source for this embroidery style effect. Add a movie file in top, then select your desired video from the file parameter on the right side. This clip will serve as the base for the entire cross-stitch texture, so please make sure the playback is working correctly before moving on. Next, we add an info chop to extract the width and height of the input video. The info chop allows us to read various properties from the connected top, and in this case, we are using it to access the rex and resi values. Next, we add a null to stabilize the output from the source video. Now, to create the pixel-based grid that serves as the foundation of the embroidery effect, we add a resolution and lower the image resolution. In this step, we use the resolution values obtained earlier to create an automatically resized version of the input, suitable for the stitch pattern. The info chop values rex and resi are first stabilized through a null chop, then passed into a math chop where we scale them down to the desired resolution. These computed values are then exported into the width and height fields of the resolution, forcing the image to be sampled at this coarse resolution. This gives us a strong pixel block foundation, which is essential for generating the stitch pattern later on. This stage essentially defines the base structure of your embroidery effect. Now that the image has been downsampled to a very low resolution, we use a fit top to scale it back up to the original canvas size. After reducing the image to around 64 by 36, the pixel blocks become extremely pronounced. To work with this image in the full resolution pipeline, we upscale it using the fit and match it back to the original resolution, for example, 1280 by 720. A key step here is setting input smoothness and viewer smoothness to nearest pixel. This prevents any smoothing during the upscale process, allowing each pixel block to remain crisp and clearly defined. Once this is done, the image is fully prepared for the next stage, applying the stitch pattern that will form the embroidery effect. Now that we have the upscaled pixel image, we proceed to clearly redefine the position of each pixel. To do this, we have added a Remap top. Next, we modify the VEC4 color value that defines the output color inside the fragment shader. Originally, the shader was producing a solid white color, but now we have changed it so that the color varies based on the pixel's screen position. Before using the tile, we adjust the base size of the GLSL pattern. This ensures that the stitch pattern repeats with the correct scale and proportions. Now we will adjust the tile to repeat the pattern created in GLSL. Using the tile node, we can duplicate the pattern horizontally and vertically, allowing the stitch shape to be arranged in a clean, grid-like layout. In this step, we use a lookup to remap the color information of the tiled pattern. The lookup node allows us to map new colors based on the brightness or color values of the input, helping the stitch pattern appear clearer and more defined. Next, we fine-tune the scale and alignment of the repeated stitch pattern using a transform top. Here, the scale values are divided by the rex and resi values from the math chop, ensuring the pattern spreads evenly across the entire image. In this step, we use the Repeat tab of the transform to refine how the pattern fills the screen. Adjusting the tile U and tile V values controls how many times the stitch pattern repeats horizontally and vertically, allowing you to fine-tune the overall density and arrangement of the grid. Now we connect the finished stitch pattern to the Remap top. This step lets the Remap node place the pattern correctly across the screen, using the original pixel coordinates to ensure accurate mapping. In this step, we use the reorder to rearrange the color channels of the input image. This allows us to isolate the brightness information needed for the stitch pattern and prepare the data cleanly for the following compositing stages. Now, we use a level to refine the brightness information used for the stitch pattern. By adjusting the black level, brightness, and gamma values, we enhance the areas where the stitches should appear and prepare a cleaner contrast for the upcoming compositing stage. In this step, we use the edge top to extract outline details that enhance the stitch pattern. By detecting edges based on luminance and increasing the strength, we make the stitch shape stand out more clearly. This edge information plays a key role later when the stitch texture is combined with the base pattern. In this step, we use the lookup to combine the edge data with the refined brightness map. The lookup node samples values from the second input based on the luminance of the first input, allowing us to control how strongly each stitch appears depending on the brightness of the image. In this step, we use the math top to refine the lookup output into a clearer black and white mask. By adjusting the range or clamping the values, we remove midtones and isolate only the areas where stitches should appear. This sharpened mask will be used as accurate placement data in the next compositing stage. Here we use the Add Top to merge the cleaned mask math 2 with the stitch pattern coming from Remap 1. The Add node strengthens overlapping areas, which makes the stitch pattern appear clearly exactly where the mask indicates. This step unifies the placement map and the pattern shape into one composite. Here we use the slope to bring out the directional detail of the stitches. The slope node analyzes the gradient of the input and remaps the values based on horizontal or vertical luminance changes, making the stitch texture look more dimensional and fabric-like. In this step, you use the math top to finalize the overall brightness and contrast. The slope top adds extra direction and micro details to the stitch texture. However, this effect is optional, so you may turn the slope node on if you want more detail, or turn it off if you prefer a cleaner and simpler pattern. The slope is simply an optional enhancement step. In this step, you connect the movie file in top to the second input of the remap node. This allows the Remap top to apply the original video's color onto the stitched pattern created earlier. The Remap node keeps the structure from the first input while using the color from the second input, effectively combining stitch shapes plus original color into the final embroidered look. This step uses a level top to refine the tonal balance, adjusting brightness, gamma, and contrast to cleanly shape the final stitched pattern. In this step, we use a rectangle top to fine-tune the overall brightness when the result feels too dark. By adjusting the box color, the stitched pattern subtly brightens only when the source video becomes slightly lighter, creating a more organic and responsive look. In this step, we connect a select top to the final math top so the output can be properly composited. The select node lets us choose exactly which top stream we want to pass into the final blend stage, in this case, the processed base video. By routing it through math, we ensure the stitched texture and the original footage are combined cleanly and consistently in the final output. After the null top, we pass the image into a resolution top to upscale it back to a higher resolution. This restores clarity after all the low-res pixel-based operations, allowing the final stitched pattern to look clean and detailed at full size. You can also add an RGB contrast node at the end to create a completely different color mood. By shifting each color channel, you can get more stylized or experimental results, so feel free to play with the parameters and explore variations. You can also add a bloom node to introduce a glowing, dreamy effect on top of the pixel stitch pattern. By adjusting parameters like glow intensity or threshold, you can dial in anything from a soft ambient glow to a stronger, more surreal highlight. This step prepares the final output in the same way we set up the export earlier. We connect the process top to a movie file out node, adjust the resolution and FPS, and set the file format so the stitched effect video can be rendered properly. Great job making it all the way to the end. In this tutorial, we went beyond simple pixel manipulation and built a complete digital embroidery / cross-stitch effect, from GLSL pattern generation, remapping, detail blending, tonal control, all the way to final render output. Every step can be customized, so feel free to adjust the colors, patterns, and density to match your own artistic direction. This effect works beautifully in music videos, motion posters, visualizers, and many other creative contexts. As always, don't be afraid to experiment. Tweak the nodes, explore variations, and create your own signature version. Thanks so much for following along. More advanced projects and updates are available through the membership, and if you have any questions, I'm always happy to help. This is Xtal signing off.